Okay, welcome back, everybody. So, um, yesterday, last lecture, we ended with a discussion of the Fibonacci numbers. Fibonacci numbers being defined by this recurrence relation here. Um, this is one of the best and most commonly used example of, say, like a linear recurrence relation. So linear here referring to the fact that the kth term in this sequence is related linearly to the terms that come before it. So what do I mean by that? I mean that this is a linear expression in these terms. So what would be an example of like a nonlinear expression? Let's just I'm just going to write here as an aside. Let's say we had some numbers that weren't like Fibonacci numbers. There were some other type of numbers. We'll call them, like here, instead of f sub k, I'll call them h sub k. And these numbers were also generated via recurrence relation like this, but the recurrence relation was something like this instead. Here, we'll make it even worse. We don't need that. That it would have already been nonlinear. This would have been example. This is an example of a nonlinear recurrence relation because this does not depend linearly on the terms that came before it. This squared term isn't even needed. The fact that I'm multiplying these two, this is already a nonlinear term with respect to these previous entries. Adding these two things is fine. Having a constant multiplying these things is fine. But having these things multiplied or raised to powers, maybe, this thing is multiplied by itself, this thing is multiplied by f sub k minus 3, that is no good. Okay, so that is what makes this would be an example of a nonlinear recurrence relation. And the reason I'm making a distinction is because we are going to see now examples both of another linear recurrence relation, and we're going to see how similar our analysis in that case is going to be to what we did with the Fibonacci numbers. And then we're also going to see an example of a nonlinear recurrence relation and think about what we might need to do in order to deal with this nonlinearity, how this might affect things differently. So in the case of the Fibonacci numbers, we were able to use this recurrence directly in the generating function to come up with a nice closed form expression for all the Fibonacci numbers in terms of these. This is like the golden ratio, and this is like its conjugate, dual, whatever you want to call this, right? So this was 1 plus, phi was 1 plus root 5 over 2, and phi hat is 1 minus root 5 over 2, which is the same thing as phi minus 1. So this is the deal here, okay? So, question, right? So, what exactly did we do? What was the idea? The idea was to substitute in that recurrence relation into the generating function, right? So the idea was substitute the recurrence relation into the generating function. So that was how we were able to get this form for the Fibonacci numbers that we did. And so I want to talk about recurrence relations more generally. And our first example illustrating this will be the Tower of Hanoi game. What is this? You may have seen this before. The idea here is you have 3 wooden poles or stakes. And around one of these, so these typically will have a base, so we'll say this is in the ground. There we go. Around one of these poles, you have the actual game pieces, which are the circular discs that have holes drilled in the middle of them so that they can be slid along these poles here. And so here's the first piece of some radius, and then there's a next piece which is slightly smaller in radius, and then the next piece. The next piece, I know I don't have these going directly down the middle. It's because I did a bad job drawing this. It's fine. It's fine. We'll say that that does it. You get the idea here. Okay. Now, so each of these pieces have differing radius, and here's the smallest, here's the next smallest, and so on all the way. Here's the piece with the largest radius. So these are these flat circular discs that have holes in the middle of them so that they can be slid down these poles. Now, the rules of this game are as follows. I'm only allowed to move one disc at a time. So only one disc can be moved at a time. That's number one. Number two, you can put a disc on any of the poles. But nowhere else. So when you are moving a disc, you don't have the option of moving it and then holding it in your hand, putting it down, not on the poles. It's got to go onto a pole. Okay. And the last rule, a larger disc cannot be placed on top of a smaller one. Now, let's say that we have K such disks. The goal of the game is to move all of the disks onto another pole. So what we mean by this, of course, is if we call this the initial pole, this is our starting position. The goal is to move all of these disks in this manner to one of the other poles. Okay. Following these rules at every step. Obviously, related to this is the question, well, how many moves are required to move the entire stack of K disks onto another pole? Okay. We're going to let A sub K denote this number. So, if I have a stack of one disk, moving it onto another pole can be done in a single move. So, A sub 1 is clearly equal to 1. Now, to move k disks onto another pole, we must first move the k minus 1 top disks to one of the other poles. Then move the stack of k minus 1 disks on top of that disk after I've moved it. Let's go back here. Here's my whole stack of k disks. Let's suppose in this process I have moved these k minus 1 disks somewhere else on either of the poles. I could then move the bottom disk to the pole where they are not, and then move them onto that bottom disk. Right? So, and think about how I do this step by step. When I do this, so move k disk, first move the k minus 1 top disk to one of the other poles. All right, so say that we've done that. Then move the bottom disk to a third pole. Then move the k minus 1 disks on top of it. Okay. So, what does this mean for a sub k? However many moves it takes me to move k minus 1 top disk to another pole, I know what that is. That's a sub k minus 1. Then I need to move the bottom disk to another pole. That's one move. Then I have to move the k minus 1 disks on top of that. That is the same as the moves required to move k minus 1 disk to another pole, but that's just a sub k minus 1. And this will finish this process. In fact, this is like the way this is done. So first, I move the k minus 1 top disk to one of the other poles. How many ways are there to do that? A sub k minus 1. Then I move the bottom disk to another pole. 1 is how many moves I add in there. Then I have to move the k minus 1 disk on top of it. That's the same as how many ways are there to do that, or how many moves does it take to do that, rather. This would be a sub k minus 1. It would be the same as the number of moves required to move it onto another pole. Okay, we just don't care that that bottom disk is already there, right? This is the same. This is the same number. We can simplify this, of course, to 2 times a sub k minus 1 plus 1. And this is going to be true for k greater than or equal to 1. So this is the relationship we have. Note, this is also a linear recurrence relation. So just like in the case of the Fibonacci numbers, I get a different recurrence relation. It is linear because it is linear in the previous terms in the sequence. Okay. This generates, starting with a sub 1 equals 1, this generates the whole sequence. So a sub 2 in this way is 3. A sub 3 is 7, because this would be 2 times 3 plus 1, so 7. A sub 4 is 15. You see the pattern yet? Pattern is easier to see in this form than the Fibonacci numbers. In fact, it's clear that the number of moves required to move k disks onto another pole is 2 to the k minus 1. Quick note, if, say, k is equal to 64, so 64 disks, it would take 2 to the 64 minus 1 moves to win the game, which, if each move took 1 second, would amount to several times the age of the universe. In time. So there's a legend about this game, because of course this fact was known, is that in a temple somewhere hidden in a jungle, there's a group of monks that is doing this game constantly using a giant configuration of some number of disks, maybe 64, maybe a little less. And when they finish the game, that's the end of the world. That's the apocalypse. And of course, if they're using 64 disks, then we got plenty of time left, so it's fine. So, in this case, to get this nice closed form expression for this, it wasn't really necessary. Now you could say, wait, this just looked like this. Do I actually know this? Well, you can try to prove it if you like. Use induction maybe, try to prove this. But our interest then is in general linear recurrence relations. Maybe I'll wait till the next page to write the general form here. So you can do this with induction if you want. But actually we're going to see a way to deal with even more general recurrence relations, and going to see what that amounts to in terms of our generating function analysis. So let's say we have the following. Say we have a general recurrence of the form we'll say a sub k is b times a sub k minus 1 plus c for k bigger than or equal to 1, where b and c are constants. This is another linear recurrence relation, just like the Fibonacci recurrence. If c is 0, we call this recurrence a homogeneous recurrence. If c is not 0, we say it is inhomogeneous. Let g of x be the generating function for this sequence a sub k. Then the idea is, by definition, g of x is the sum over k non-negative of these terms in the sequence as coefficients of x to the k in this power series. Now, I have this recurrence relation for k bigger than or equal to 1. Just like for Fibonacci, then, I want to pull off any terms of this generating function where I don't have the recurrence. Maybe your recurrence starts for k bigger than or equal to 5, right? You could pull off every term before that and separate it in the sum. It's a finite number of terms like that. Here, I'm only going to pull off the first one because I have this recurrence relation for k bigger than or equal to 1. So this is a naught plus the sum k bigger than or equal to, 1 here, a sub k x to the k. So now I can substitute in this recurrence into my generating function here, since I'm in the case k bigger than or equal to 1. So this is a naught plus the sum over k bigger than or equal to 1 of this expression. So b a sub k minus 1 plus c times x to the k. Just like in the Fibonacci case, I'm going to multiply, I'm going to distribute this x to the k and split this sum. So this was a naught plus, here, this is going to be the sum for k greater than or equal to 1 of b a sub k minus 1 x to the k plus c times the sum, or k bigger than or equal to 1, of x to the k. Now, this is, let's see about reindexing here. I can reindex here. I can, yeah, let's just do it step by step here. So reindexing, I'm going to, if I reindex starting at k and pull an x out. So if I reindex this, replace k minus 1 with k, this sum starts at 0, pull this extra copy of x out of the sum, so that this would be b times x times the sum k greater than or equal to 0, a sub k x to the k. The reason why we're seeking this is exactly what g is. Plus, I'm going to put this starting at 0 and move a copy of x outside. So this would be cx times the sum k greater than or equal to 0, x to the k. So here, this is g, and this is geometric series. So what we are getting out of this is that the generating function, when these a sub k's satisfy some recurrence relation, satisfy some kind of recurrence relation in the generating functions where it depends on an expression involving itself here. So this would be a naught plus bx times g of x plus cx times 1 over 1 minus x. So this would be plus cx over 1 minus x. And this is our expression here. So then solving for g, remember we started with g of x is equal to this, so let's rewrite that up here. Our generating function g of x is a naught plus bx g of x plus c x over 1 minus x. If I move this term to the other side, factor out a g, this would be 1 minus b of x g is equal to a naught plus cx over 1 minus x. So that g of x is, I'm going to write this term first, so this is cx over 1 minus bx times 1 minus x plus a naught over 1 minus bx. Okay. Using partial fractions here if you like, if b is not equal to 1, we can split this. So cx over 1 minus bx times 1 minus x can be written as c over b minus 1 times 1 over 1 minus bx minus 1 over 1 minus x. Thus, g of x, let's put this in here, right? This is then, so putting this here and distributing this, there's a 1 minus bx here, there's an a naught over 1 minus bx here, so I can pull out the c over b minus 1 plus a naught times 1 over 1 minus bx minus c over b minus 1 times 1 over 1 minus x. So that's from distributing here, putting this in my formula for g. How does this help me? Well, actually, these are the right-hand side for geometric series. This is the geometric series sum. Both of these are. This one, the thing is bx. This one, the thing is just x. And so, g of x is, all right, it is a naught plus c over b minus 1 times, this sum is, this is the geometric sum with bx plugged in. So this would be bx to the k in every term, which would give us b to the k, x to the k for this sum, minus c over b minus 1 times the sum over k not negative of x to the k. Here's our expression for g. But a to the k, or sorry, not a to the k, a sub k is the coefficient of x to the k in this generating function. Therefore, what is the coefficient of x to the k here? Well, I can just read it off. It's going to be a naught plus c over b minus 1 times b to the k minus c over b minus 1. Let's rewrite this on the next page. This is what we claim. This gives us a very nice closed form expression for these a sub k's. Recall that we started only with the generic recurrence of this form, which gave me, of course, an expression for a sub k in terms of previous terms in the sequence, using generating functions and the exact same sort of analysis I did for Fibonacci, for the Fibonacci sequence. I get this nice closed form expression for this a sub k, but let's see that this actually works. Okay, so Tower of Hanoi. Our relationship was this, but we saw for the Tower of Hanoi, this relationship was the following. So B is 2 and C is 1, right? B is 2, C is 1 in this example. So B is 2, C is 1. So if A naught is set to be 0, a sub k is going to be 0 plus 1 over 2 minus 1 times 2 to the k minus 1 over 2 minus 1. This is 1 over 1, 2 to the k minus 1. Oh. Well, this wasn't proved before, but now it is. So you can view this as a proof of the Tower of Hanoi fact that the number of moves required to move those k disks onto another pole is 2 to the k minus 1. You could have also proved that with induction just from our formula. But here we have something that works more generally and allows us to compute this thing. Now, not just for, of course, Fibonacci sequence. So Fibonacci sequence, obviously, we had a slightly different setup. The recurrence was slightly different, even though it was still linear recurrence. But here, now we can do this for any number of problems that match this type of recurrence for the sequence in question. Okay. All right. So before I move on, I'm going to note some useful generating functions. Okay. So 1 over 1 minus x is sum k greater than or equal to 0 of x to the k. This is our geometric series formula. This is our method for computing a geometric series sum. We can differentiate both sides. You can term by term differentiation here, and we're doing all this formally. We don't care about convergence issues. We'll worry about that later if we worry about it at all. So differentiating here, of course, I get immediately, if I differentiate the left-hand side, this is 1 over 1 minus x squared, because of the minus. And this is equal to, if I've differentiated this, term-by-term differentiation of a power series. Again, your favorite Calc 2 fact. This would be k times x to the k minus 1 here, right? So this tells us a generating function of this form, which of course, multiplying both sides by x, I get x over 1 minus x squared is multiplying by x, incorporating that into the sum. This is the same as starting the sum at 0. K x to the k. And so this is the generating function for the identity sequence, right? So quick example, if a sub k is equal to k for all k, then the generating function g of x for the sequence k is exactly, right? What is this on the right-hand side? This is just the generating function for the sequence a sub k equals k. So this is x over 1 minus x squared. Okay. You might ask the question, what is the generating function for the sequence k sub n, or sorry, not k sub n, k to the n, k raised to the nth power, for some fixed n. And we'll do this later. Okay. Now, one more. What if I integrate both sides of this expression? So I differentiated both sides to get an expression for the generating function of the identity sequence. What if I integrate both sides here? What am I going to get? So integrating, again, I can talk about integrating term by term in a power series. I get that, of course, on the left-hand side, so that my dx matches up, this would be minus the natural log of 1 minus x. Okay, and that is equal to, integrating here, this is going to be sum k bigger than or equal to 1 of 1 over k times x to the k. So what this says is if a sub k is 1 over k for all k, then g of x, the generating function for the sequence 1 over k, is minus the natural log of 1 minus x. Okay. So these are two new generating functions that you can view as canned. When you are in a situation where you would maybe need such a generating function, here you have it. Okay. In both of these examples. Okay. So moving on. There is a very nice application of generating functions. I think this will be our last one. We're going to talk about what are called Catalan numbers. So here's a question. How many ways are there to compute a product of k plus 1 matrices? So first of all, we should note, of course, that matrix multiplication is not commutative. You cannot swap the order of matrices in matrix multiplication. So matrix multiplication is not commutative in general. Of course, don't fuss at me and tell me that you have 500 examples of A times B being equal to B times A. You can definitely do that, but that's not true for general matrices. But it is associative. So when we say how many ways are there to compute a product of k plus 1 matrices, we're talking about the number of ways to place parentheses around these matrices in a different fashion. So let C sub k denote this number. Okay. Now, product of one matrix, there's only one way to do that. Product of two matrices, there's also only one way to do that. There's no way to, so in this instance I have a single matrix, so we don't even talk about that. Here I have the matrix multiplication, say A times B. How many ways can I do that? Well, there's just A times B, that's it. But what about for 3? So what about, oh, wait a minute, I'm doing something wrong here. C sub 1 is a product of 1 plus 1 matrices. So this is 1. This corresponds to C sub 1 here. So in this instance, we're talking about a product of 2 matrices. So C sub 1 is 1. There's only one way to do this. C sub 2, however, there's matrix product ABC. We could do A times B times C, or we could do A times B times C, like this. And those are the only ways. I'm not allowed to do A and C multiplied by each other first, because that would mean swapping the order of the multiplication. I'm not allowed to do that. So I can place the parentheses around pairs in this way, right? I can place parentheses like this, but I can't change the order of the letters. Notice if I'm reading left to right, the letters are A, B, C in both cases. There's 2 ways of doing this. Okay, for C sub 2. Okay. What about 4 matrices? So C sub 3. What is this? So I have 4 matrices. We'll say A, B, C, D. Right? Okay. So how can I group these? I could do A, B, C, D, like this. I could group them as A, let's do BC first, and then multiply that by A, and then we multiply D. That's another way of doing it. Okay. I could do a similar thing except with D, so okay. I could do A times B like this and group that with C. I could do A times B times CD. And thinking for a second, I realize, oh, this is all of them. This is all of them. There are 5 such ways to do this. There's no other product I can do. There's no other way to associate these things that will make it work. Turns out, I'm not going to do it by hand, that C sub 4, so the same question for 5 matrices, it's 14. That is 14 ways to multiply 5 matrices. Okay, so let's just record our results here. When k is 0, this corresponds to the product of one matrix, so there's one way of doing that. When k is 1, this is how many ways you can write the product of 2 matrices. Again, there's only one way of doing that. When k is 2, there were 2 ways to multiply a product of 3 matrices, so this was 2. When k is 3, there are 5 ways to multiply 4 matrices. When k is 4, there are 14 ways to multiply 5 matrices in this way. And then the question, can we determine a recurrence relation for these numbers C sub k? So here's a start. But do we see a way to notice how the previous terms in this sequence of numbers tells you something about the next term, right? You might already be thinking in terms of that just because of how many ways there are to reassociate like sub-blocks of matrices here, or sub-strings of matrices. So let's denote matrices just by x sub I. So denote matrices by like x sub I. We're just going to use lowercase x sub I here to determine these matrices. And so suppose, I'll write it here. Suppose we group the terms so that the last multiplication occurs between x sub I and x sub I plus 1. So if we have done that, it means that I have a list of matrices, which I'm going to list x0, x1, and so on, up to an x sub I. And then x sub I plus 1, x sub I plus 2, and so on, up to k. So notice that the order of the x sub i's doesn't change when we are doing this reassociating, this moving of the parentheses. Okay, so doing this moving of the parentheses, the order of the x sub i's doesn't change. The only thing that changes is our placement of parentheses around them in this way. Okay, so say that we've done this. This is exactly k plus 1 matrices. I'll write it here. Okay. So, how do I relate the Catalan number C sub k to the Catalan numbers for these subgroupings? Well, how many ways are there to group the terms in the first part? I'm going to write this again. I'm going to write this at the top here. Okay, this is how we've done the grouping. There are C sub I ways to group the terms in the first part of the product. And then there's however many remain, which is C sub k minus 1 minus I. Right? So C sub k minus 1 minus I ways to group the terms in the second part. So using our product rule, we're doing this in sequence. So this means there are C sub I times C sub k minus 1 minus I ways to group the remaining terms. Okay. Summing over the I, where this happens, where this cutoff happens, if we sum over this process by our sum rule, right, this will exhaust all of the possibilities here. And so summing over I exhausts all possibilities here. Thus, the number, so the total number of ways to group k plus 1 matrices is, we called that C sub k. That was defined as, that was defined as the total number of ways to group k plus 1 matrices in this way. But according to this, this is a sum over I of these. So it is a sum from I equals 0 up to k minus 1 of C sub I times C sub k minus 1 minus I. And this is what we get for k greater than or equal to 1. Now, this is in fact a recurrence relation. Okay, so we asked, can we determine a recurrence relation for C sub k? And the answer is yes. I'm going to work out a few of these, but then I'm going to ask what a potential problem is here. Right, so let's work this out ever so slightly. So what is C sub 1 here? This is, according to this should be C naught times C naught, which C naught is here. C naught is 1, so this would be 1 times 1, or 1. That is exactly what C sub 1 should be. All right, what about C sub 2? C sub 2, according to this sum, should be C naught times C sub 1 plus C sub 1 times C naught, which is 1 plus 1, or 2, which is exactly what C sub 2 should be. C sub 3, again, according to this expression, is C naught plus, times C2 plus C1 times C1 plus C2 times C naught. This is C naught times C2 is 1 times 2, 1 times 2, 1 times 1. So this would be 2 plus 1 plus 2, which is 5, which is exactly what C sub 3 is. And one more, just to do it. C sub 4 is C naught C3 plus C1 C2 plus C2 C1 plus C3 C naught, which is C naught C3. This is 1 times 5 plus C1 C2 is 1 times 2, 1 times 2, 1 times 5, which is 14, which we said this was just check that C sub 5 is equal to 42 using this same recurrence. Okay. All right. Now, one thing to note, this is a nonlinear recurrence. We are going to try to use this in the same way, but we need a little bit of extra algebra help. So note, this is a nonlinear recurrence relation. What does nonlinear mean here? Again, it means that the terms, when I say that C sub k depends on the previous terms in the sequence in this fashion, it is not linear in those arguments. It's not linear in those terms. So you are multiplying these terms together. This is not a linear thing. It's like you're squaring them, right? This is, you're multiplying some of the previous terms together here. And so this is an example of a nonlinear recurrence relation. We can still use the same trick with generating functions. We just need a little bit more algebra help. So now we wish to use generating functions to solve this recurrence for a formula for these numbers, C sub k. To that end, let's say that g of x is the generating function for these numbers. So there it is. So, because this is nonlinear, one of the things you get is that the number of terms in these is going to change, right? So it changes at each step. That didn't happen with the other recurrences that we had, right? We didn't have this variable number of terms here. So I need a fact. So what do I need? So here is, we'll just call this fact. If a of x is a generating function for some sequence. We'll say a sub k. And b of x is a generating function for some other sequence, say b sub k. Then the product of their generating functions can be done in the following way. This is a sum over k greater than or equal to 0 of a sum over I, so this is I from 0 to k, of a sub I, b sub k minus I times x to the k. And so if we let c sub k be defined as exactly these coefficients of the x to the k term in this product of the generating functions, then the sequence c sub k is called the convolution of the sequences a sub k and b sub k. So a way to state this fact is that the generating function of the convolution of two sequences is the product of the generating functions of those sequences. Okay. Okay. We're going to need this fact. This is unavoidable, and it's unavoidable because this relation that we are looking at is nonlinear, so I'm going to need to use this. Okay, so using this, let's start like we always do. Let our generating function g be exactly what it's defined as, which is sum over these Catalan numbers c sub k, x to the k. Using this recurrence relation, I plug that into my generating function here after peeling off the first term, as I've done in all of these cases, from the Fibonacci case, the general linear recurrence, or not completely general linear recurrence relation, but the one that we did previously. And then in this case, this is true for k greater than or equal to 1. I need to peel off the first term here, so this would be c naught plus the sum k greater than or equal to 1 of sum from I equals 0 to k minus 1 of c sub I, c sub k minus 1 minus I times x to the k. I've just directly imported that expression for the c sub k's here. Okay, that's all I did. Okay, now reindexing and pulling out a copy of x here. Of course, c naught is just 1, so this is 1 plus x times, I've reindexed here so that I'm starting at k equals 0, so this is k greater than or equal to 0, of these expressions. This is sum from I equals 0 to k now of c sub I, c sub k minus I, x to the k. I did all this reindexing so that I can look at this and say, wait, this is just my generating function. But it's my generating function times itself, right, by this fact that the generating function of the convolution of two sequences is the product of the generating function of those sequences. Here, the convolution of the two sequences involved are two of the same sequence. They're just both the Catalan numbers, right? So this is the product of the generating function times itself. So this is 1 plus x times g of x squared, because of this convolution bit. This is actually the sequence c sub k convoluted with itself, c sub k. So that is product of the generating function with itself. Okay, so this is convolution of this, I should say, these. This is convolution of c sub k with itself. So moving this to the other side here, this I get x g of x squared minus g of x plus 1 is equal to 0. So I guess just move g of x to the other side. That's fine. Use quadratic formula. We can use the quadratic formula to solve for g of x. Don't get shocked by this x here. This is a quadratic in the variable g, if you like, right? So that g of x is 1 plus or minus the square root of 1 minus 4x over 2x. So check that we did the quadratic formula correctly. 2a, that's 2 times the coefficient on the x squared term, in this case the g squared term. So that's 2x, yep. We have minus b, it's minus 1, so minus minus 1, plus or minus square root of b squared, minus 1 squared, minus 4ac, ac is x times 1. Yeah, that's it. All right, so that's it. Now, this gives us two functions, right? So only one of these can actually be the generating function. So what has to be the case? So note the limit as x goes to 0 of g of x must be c naught, or rather is c naught, which is 1. And so that needs to match up with this. This only matches up if I take the minus here in this quadratic formula. So g of x is 1 minus the square root of 1 minus 4x over 2x. This is the one that actually makes sense. Okay. Now, I want to expand as Maclaurin series and compare coefficient of the x to the k term. So let's do that. So I'm going to use the generalized binomial theorem and along with this, the negating the upper index. These were two facts that I stated back to back when we used them a couple lectures ago. In this way, the term that is tricky here is simply this radical term. So I want to deal with this radical term, then dividing through by 2x is no problem here for figuring out this power series. So that radical, what is square root of 1 minus 4x? If I'm going to write that as power series, I'm going to, using the generalized binomial theorem, rewrite this as 1 minus 4x to the 1/2, which by our generalized binomial theorem, this would be the sum over k non-negative of 1/2 choose k times minus 4x to the k. Using the negating the upper index bit, this becomes the sum over k greater than or equals 0 of k minus 3/2 choose k times 4 to the k x to the k. I got rid of the minus 4. The minus 1 to the k got absorbed when I used this negating the upper index formula, or identity rather. I am going to peel off one term here, so the k equals 0 term, this is going to be 0 or 1, sorry, plus the sum k greater than or equal to 1 of k minus 3/2 choose k times 4 to the k x to the k. Reindexing here, pulling a copy of x out, my standard trick. This is 1 plus, I'm going to move a copy of 4 out as well when I do this reindexing, so I'm moving 4 and x out, which would replace these with 4 to the k minus 1 and x to the k minus 1, but I'm reindexing starting at 0, so this would be 4x times the sum k greater than or equal to 0 of k minus 1/2 choose k plus 1, 4 to the k x to the k. You might say, well, why did these change? Because of this reindexing. So again, if you want to do the reindexing, you're pulling out a copy of 4 and x. That replaces these k's with k minus 1s. Then you're replacing k with k plus 1 and starting at 0. So then k becomes k plus 1, k minus 1 becomes k, and then k minus 3/2 becomes k minus 3/2 plus 1, so this would be k minus 1/2. Okay. So, combining these all together now, back, this implies that g of x is, so this is just the root 1 over 4x term. G of x is this. It is 1 minus the square root of 1 minus 4x over 2x. So how do I use this? This is the expression I have here. So then 1 minus this expression, and then I'm dividing by 2x. So the 1's cancel. I'm left with this expression. I'm dividing and I'm subtracting it, so there's a minus here, and I'm dividing by 2x. So this becomes minus 2 times the sum, k greater than or equal to 0, of k minus 1/2, k plus 1, 4 to the k, x to the k. Do you see where this comes from? G of x is 1 minus root 1 minus 4x over 2x. Root 1 minus 4x is exactly this expression. When I do 1 minus this expression, I get 1 minus 1, so that's 0, and then minus 4x times this expression. Then I'm dividing by 2x. So I would get minus 4x divided by 2x times this expression, which is just minus 2 times that expression. Okay. Thus, what this means is that I have now found a closed form for my Catalan numbers. They are, in fact, putting all these things together, these are going to be minus 2 to the 2k plus 1 times k minus 1 half, choose k plus 1. Okay. Now, there is a better form for this. This isn't the absolute best form that we can find for this, so we can do better. If you are like, oh my God, why are we computing these Catalan numbers? Why are we spending so much time on these things? Maybe if you weren't wowed over by the description of these things as being the number of ways to do k plus 1 matrix multiplications. There's another characterization I will give you of these Catalan numbers here in just a few minutes that will maybe pique your interest instead. So, to do better, okay, let's expand the generalized binomial coefficient So expand the generalized binomial coefficient that we have and multiply each coefficient, or sorry, each term in the product by 2. What do we get? So C sub k, we wrote it as this thing before. Another characterization is this is minus 2 to the 2k plus 1 over k plus 1 factorial times the product from I equals 0 to k of k minus 1 half minus I. This is just me doing what I said here. Expanding generalized binomial coefficient, expanding this thing directly, and multiplying every term in the product by 2. This is what I get here. I can then distribute one of these 2's here, multiplying every single one of these things by 2. This would be minus 2 to the k over k plus 1 factorial of product I equals 0 to k of 2k minus 1 minus 2i. Okay. So here I have distributed I've distributed these 2's, these k2's, to every term in the product here to get rid of them here so that what I'm left with is 2 to the k. Okay. But what is this product? This is the product of all odd numbers between minus 1 and 2k minus 1. think about why that is. So then this is 2 to the k over k plus 1 factorial times the product starting at 1, ending at k of 2I minus 1. This is just a better way of writing this product so that these are the exact same thing. Okay. Being clever about how we rewrite this, this is 2 to the k over k plus 1 factorial times product equals 1 to k of, I'm going to write this as 2I minus 1 times 2I over 2I. Specifically, to move one of these things outside, I'm going to move this 2I here in the denominator outside. If I do that, this is 2 to the k times k factorial in this whole product. So this would be, moving that out, this would be 2 to the k over 2 to the k. There's k copies of this 2 in this product. And then I multiply I, which is, I multiply 1, 2, 3, 4, 5, 6, 7, all the way up to k. So that's k factorial. And this is all times the product from I is equal to 1 to k of 2I minus 1 times 2I. Okay. So we're almost done here. The 2 to the k's cancel. And I'm left with 1 over k factorial times k plus 1 factorial times this product equals 1 to k of 2I minus 1 times 2I. But this product is actually just 2k factorial. And so this is really 2k factorial over k factorial times k plus 1 factorial, which can be written as 1 over k plus 1 times 2k, choose k. And so, rewriting these entirely, I'm going to write that expression again. So one way of writing this is 2k factorial over k factorial times k plus 1 factorial, which is the same as 1 over k plus 1 times 2k, choose k. These are the Catalan numbers. Now, to end our discussion here, I mentioned that these are important. These show up quite a bit. In a way, these are like the second most, so maybe we'll say these are the second most, should I say popular, frequently occurring numbers in combinatorics. What do you think the first most frequently occurring numbers are? The binomial coefficients. Just the straight up binomial coefficients. But aside from the binomial coefficients, these have been claimed to be the second most frequently occurring numbers to show up. So, in fact, the c sub k is always an integer. So in fact, we have shown that k plus 1 always divides 2k choose k, since c sub k is always an integer. Okay. You were worried about it being negative, right, when I first slapped a negative sign in front of it, right? But remember, we have the generalized binomial theorem. These products involved are a little different. There was actually no negative there at all. Okay. So there are many combinatorial interpretations of these numbers. I think in fact, there's a textbook that lists about 66 different ones. So we'll say at least 66 different ones. So many types. But let's see an example of one. You know, maybe been lecturing for a while. I'm already over by a couple minutes, so maybe I'll leave this. So we will see one more Catalan number example next time. So the thing that I promised you earlier, that if you weren't interested in Catalan numbers now, might win you over, that'll have to happen next time. So at the beginning of next lecture, I'll talk about this specific example before moving on out of generating functions. But hopefully by now this has given you a good enough understanding that these generating functions are very useful. So that in the service of counting, answering a lot of these questions that we had about various counts, generating function was extremely useful when you had a recurrence relation. It was extremely useful in other sorts of settings. So I've tried to give like as wide a breadth of examples as possible with all of these things, so that when you're thinking about some of these problems later, you can maybe think to yourself, oh yeah, I can use a generating function to do this. So anyway, that is all for today. We'll start here next time. So I will see you all then.